Good morning, everybody. Looks like I got 10 o'clock here. Thank you for joining us for another long coffee break, Thursday morning coffee break. And this morning, we're joined by Dan Evans, the Vice President of Sales and Channel for CRC. And Dan's going to be talking to us about CRC's closed loop Venturi valves. Dan, thank you for joining us this morning.
Good morning. Good morning. All right. Aaron, am I good to take over?
Yeah, go ahead.
Let's see, hopefully. All right. Good morning, everybody. As noted by Aaron, Dan with CRC, I'm going to take the little coffee break with you guys this morning and talk to you a little bit about air valve technology and most impactful, the air valve technology by CRC, which is our closed loop Venturi. So we're going to talk a little bit about the technology and then kind of what that means for us for implementing it in space and using it in space. Closed loop Venturi, the CLV. So the CLV is designed for airflow measurement. So what it is, it's available to provide us flow measurement and control, but also take into account that static in our system is one of the areas that we're looking to make sure that we optimize and control. So it has a very low max pressure drop of 0.3 of an inch. And we'll talk about that a little bit more as we move forward. It is flow feedback. And what we mean by flow feedback is it's flow feedback by air measurement. So it does measure airflow and then give us what is that true CFM coming back as a measurement, and it's not a derived value or a metered style value coming back. So there's some things we can do with that. Whenever we hear measurement, we usually hear things that pop up, and it comes into play with, well, what do I need to take into account from a design for my inlet or outlet? Well, one of the nice attributes about the CLV and how it operates is that it has zero entering or leaving duct requirements. I got some good data on that, but it's really one of the things that gives us some flexibility for putting it into space. Mounting in any orientation, this comes up when we talk about what we do from a design standpoint. You know, do we have any kind of product that as we're designing or we're laying it out or we're anticipating the project, do we need to pick, does it need to be horizontal, vertical, or have its placement? Really with the CLV, there's no need to have that level of depiction at design because it can be mounted in any orientation, whether it be vertical, horizontal, on a 45-degree angle. Pressure independence. It is a pressure independent air valve. Why is pressure independence important? Well, one of the biggest things is, and we're going to talk about it a little bit, is when we get into these spaces, we're trying to control airflow and manage airflow. So one of the large areas that we have is how do we ensure that this envelope or this space that we're working on can stay repeatable and reliable and kind of detach us from what might be happening in the system, right? We may have some things that will cause a system to change its effective static pressure. We don't want that then to take into effect the amount of flow or volume we can move through the spaces. So the CLV is pressure independent. We talk about being contaminant or fouling free or impervious to dust, wind, and dirt. And what that comes to be is it talks about the maintenance of things. Like what do we have to do to interact with it, right? We are measuring flow, I'm giving flow feedback, and we get that area that pops up in some of our other technologies that we use. It says, well, we got to go in there so often and clean it off. With the CLV, we do not have a scheduled maintenance or recalibration as part of that. And one of the reasons being is we know these spaces, we know the access is limited, and we don't want to spend a lot of time going in and working with it in order for us to be able to achieve a certain result. Single air valve capacity up to 3,400 CFM. What does that mean for us is when we look at our ability, so we offer air valves from a 6 to a 16-inch. And then what you guys see in that chart there on the bottom is what is the design max CFM. When we say, you know, if you reached out to Long and said, what could a 6-inch air valve do? They would say, I designed it for a max CFM of 480. And that gives us a little bit of room from its actual max flow value. And at a 6-inch, you can see we can put 480 CFM through it, and then a 16 all the way up to 3,400 CFM. So one of those areas, again, having the ability to reduce the number of parts and pieces that may be together to get the similar result. All right, we're gonna do a little energy conservation. What we mean by that is a lot happens inside these systems when we hear air valves. I often hear people come back and say, well, what is the static requirement? What's my system effect? What are the things that we're going to need to try to do this? And one of the areas that comes up a lot is there's a lot of air valve technology out there that the first conversation we talk about is static pressure, right? You know, what kind of air valve is it going to be? How much inlet static or system pressure do I need in front of it for it to be able to do something? One of the things when you look at the CLV and I throw up the pressure chart, what you're going to notice is being a measurement device, it's measuring airflow and controlling to it. What you get is now as my flow changes across the, I'm going to take a 6-inch valve, goes from closed 0 CFM to 480 CFM. As that rate changes, you can see the actual static pressure or pressure loss that will exist is going to now change as our flow decreases. So it gives us some attributes that we get from a design standpoint. And one of the ones I'll throw out there, the case that we often get when we look at design or owners implementing is optimizing static. So I'm going to jump back one slide on you guys just because we're having this conversation and we can look at it. That gray bar inside the valve performance chart you guys see at the top is what we say is, keep to the optimal performance at the 10-to-1 turn down plus or minus 5%. But we can say, I want to do 400 CFM. Well, if we look 400 CFM on a 6-inch valve, if we went across then down would be about 2/10 of an inch of static pressure. Well, if I pick 400 CFM on a 10-inch valve, now what it is, I can still deliver 400 CFM plus or minus 5%, but instead of having that 2/10 of an inch, you're now down to 0.02 inches of static. So one of the ways that we can use it as a way to help through design and help through implementation. All right, so we talk about it, and this is one of the things that we're very, very passionate about because it's a big thing for design, big thing for impact when it gets into a system, and that's when we talk about no inlet or outlet. And so no inlet or outlet, what I want to have here is the CLV is tested to all the ANSI and ASHRAE standards that we may have for laboratories all the way into healthcare. And this is a third-party test that it goes through often. In this particular one, what it was a inlet and outlet test. So they were very focused on making sure, does it actually meet not needing any inlet or outlet requirements? So the chart that you guys can see on the screen right now, what you can see is across the top lists different inlet and outlet conditions. And then we had two set points. We had an 800 CFM and a 1300 CFM set point. So how this test runs is you hook up your air valve, you put 5 duct diameter straight, 5 duct diameters on the discharge, and then they balance it and validate, okay, 800 CFM, 1300 CFM. And then all that happens during the test, you don't get to interact with the air valve, you don't interact with the control sequence. All that they do is they change out the parts and pieces, whether it be on the inlet or discharge, and then record what those values are. So what you guys can see as it works across, they're going to change one at a time. So we go from straight, plenum, straight, plenum, plenum, and then work our way through our short radius 90 elbows. And through that entire test, what you can see is based on an 800 CFM set point and a 1300 CFM set point, that CLV performed within plus or minus 2.5% of their calibrated measurement stations that they had all the way throughout the ductwork. What does it look like? This is actually a picture from that test, right? So it's in a room. They got the air comes through, and this is probably some of the worst scenarios that we can see full measurement devices having to be installed inside the duct, and this is plenum in, plenum out, which surprisingly was one of the best scenarios that air valve operated in. And so I like kind of showing this and talking about it as one of the areas that truly states this air valve doesn't have any inlet or outlet restrictions. What does it mean to us? Big thing it means to us is repeatability and reliability. We have that importance of measurement. So that Venturi shape, what it does, you guys can see a cutaway of the COV here. It has a full measurement section that would be at the top of the screen, and then where we control. What we do is we use that Venturi shape for flow measurement, and we call it indirect flow measurement. What we mean by that is that there's nothing that's going to be in the center of the airstream. We're not going to have your typical flow crosses or pitos. We measure static pressure over those two different diameters to help stay away from that contamination. Speed response is one that comes up a lot. The best way that I always talk about it is, depending on the system, we may have to move quicker or slower. Most often comes into our fume hoods. So when we see speed of response, the CLV is designed to match any design criteria with fast acting response of less than 1 second to maintain set point. It measures and controls the close. What's one of the areas that impacts to? So we talk about a 10-to-1 turn down plus or minus 5%, but what's nice is you can actually take this air valve all the way down to close and still have feedback all the way down to close. So in some of our design scenarios, we may have a system that could be allowed to close off depending on something else happening inside the space. So we don't have to have that 90 CFM or 110 CFM minimum that we might see in some other technologies always going through a section just because it's that minimum flow rate. Pressurization independent. We talked before, a big thing for pressurization independent is the ability to achieve what we're looking to achieve. And that is maintain airflow in and out of the space without having that system affect us. What I bring into that contamination following freeze. When we talk about it, no schedule, maintenance, and interaction, we really mean that. Our big target is everything as you're looking through that COV, there's nothing in the airstream from a measurement standpoint that we're anticipating someone to go in and have to clean off. So we don't have to try to grab access to the system or go in and try to interact with it some way that might be challenging in these critical environments. We're talking air valves. So air valve design is a big one that comes in. We got our feedback, we got our ability to get it into space. But what I have here is some images of the COV installed in ductwork, and we see a lot of different areas that we might have. The top right photo, we see a nice truncated system or manifolded system coming down the center, and we're pulling a bunch of trunks off to go to their respective devices. Bottom right, more of a singular style, but comes into being able to meet what was that requirement of space. So we see it come out of the hood to match the other ductwork. It's going to have some transition to get back in line. But the one I talk about a lot is the large one on the left side of the screen. And that is, if you look at that, so we see a bunch of air valves coming in this particular case. What worked out well is they had very, very difficult ability to run ductwork and get their flow rates. So if we look at this back air valve that's now been circled, what you see is we come out of a fume hood at a 12-inch collar. We instantly go to our short radius 90 that turns from round to rectangle. And then we take a rectangle right into a round transition right into the front of the air valve. And so that I like to weave the mesh of this air valve from a design standpoint. We're picking CFM, and as long as we can get that arrow flow direction, we can install it in any orientation or inlet or outlet condition we can find. Air valves work together. So this is a lot where we talk about airflow and pressurization and some of the key requirements. So we have increased ACH inside these critical environments so that we can maintain what we're looking to maintain. So we know we're moving more flow. Pressurization is key, but pressurization we get from being able to keep that reliable airflow rate, volume in, volume out. We want to make sure that we're measuring things. Reason being is we have a lot of exhaust that comes in these spaces. And if I don't know what one's doing, or there's one out there that we're going to assume to do 100 CFM, but maybe it's doing 120, or maybe it's doing 90, now that impacts my entire volume in, volume out. We want to be able to measure and validate pressure. We're obviously controlling to CFM rates in our tracking, but we want to know that we have pressure there. And a lot of what it comes in to be is this image on the right. When we look at it, we have a lot of independent stations. So if I went and looked at all the exhausts that we have there, that's where we see those red dots. So we have our fume hood exhaust, we have some snorkel pickups, we just have a general exhaust sitting inside the space. Looks like a benchtop exhaust, but we see 8 red dots. All 8 red dots are working together to provide a consistent, repeatable total exhaust coming out of the space. So the sum of the parts needs to equal the sum of the whole. And one of the areas we want to ensure is when we talk about air valves or ventilation technology, we pick one that can ensure that all those parts and pieces are working together so that when we try to get to a space, we have all this exhaust come together, but what happens on the other side? We typically get into a scenario where we see this, we might only have one exhaust into the space. So now we're trying to maintain volume in, volume out with 9 independent pieces, 8 working together, 1 working to follow whatever happened to those other 8. So that's where a lot we talk in the air valve technology, being able to have that consistency or repeatability of outcome when it comes to airflow measurement and not having things that are going to impact our interaction with space. Flexibility of space. I use this because this is when we look at air valves, our lab design, our healthcare design are coming in a lot of different shapes, flavors, and sizes. And one of the areas that's there is, what are we going to be doing inside the space? How's it going to be controlled? If you look at these images, we can see that there's a vast difference. You know, bottom right, we got a lot of hood exhaust, probably heavy lab style setting. A lot of airs would be moving in and out. The top one looks like we just have a lot of bench top, so we're just going to have air, or we have a lab space where we have a lot of separated rooms. So what's going to impact us the most, but how does that also change all of our parts and pieces having to go into the space to work together? What's the purpose of the space? You know, what are the design impacts? You know, do we bring a lot of air valves into the space because we're going to have a big open lab and have a lot happening? I might have all those, some of the few working for some of the whole, or can we get to a design where it may be architecturally worked to try to do more independent, smaller spaces where we may have one or two fumes inside the space? Because the big one that's going to happen is what's going to happen to help interact the interaction inside that space, or how's that going to change our ability to use like a CLV in the space to move air in and out. I want to thank everybody. I know it is a good coffee break. I didn't have a chance to take a sip of mine, so I hope everybody else did. Big thing here, again, wanted to be able to show everybody the CLV by CRC and kind of how that works inside space and what are the things we're looking to achieve with it. And certainly if there's any more information that you guys need, please reach out to Long and we can get you guys everything for your next design or critical environment.
Dan, thank you very much. That was a lot to pack in. You know, big takeaways there for me were the 0 in, 0 out duct configuration and the 34 CFM out of one single valve. Really some big advantages there. Appreciate everybody for sticking around. And I hope you'll join us next week where Andrew Tobin will be hosting our coffee break. Join us again next week. Thank you.